Okay, so I've tried to tidy up a little bit and record the most important formulas. So we're doing like front quantization. We're going to work with x plus minus and xa. A goes from 1 to d minus 2, and x plus minus are built out of x naught and xd minus 1. The equal x plus slices are these lines of gradient minus 1. So this is the first difference to an equal time quantization. We now use different equal x plus slices to foliate spacetime. Associated to each slice would be a phase space if you're doing classical mechanics. It would be a Hilbert space if you're doing the quantum mechanics of a single particle, or it would be the Fock space if you're studying a quantum field theory. And time evolution now corresponds to x plus evolution. So as we evolve in time, we move from one slice to the next slice, to the next slice, to the next slice. So we've been studying the d is equal to 4 free massive scalar field. So there I've just summarized the formulas relating the light cone coordinates to the normal coordinates and relating light cone derivatives to normal derivatives. In terms of these coordinates, we found this expression for the Lagrangian, um, and then we worked out what was the conjugate momentum. Now, let me just make one comment. Usually when we work out the conjugate momentum, we would say pi is equal to dl d phi dot. Now, phi dot means it's the derivative with respect to t of phi. That's the old version. This is one of the things that we are replacing. What are we replacing it by? Anytime that we see a phi dot now, this now means d plus phi, because it's d plus phi that's our evolution parameter. So if you look at pi, this was meant to be equal to dl d phi dot, and because phi dot is d plus phi, it means that pi is equal to dl d plus phi. And we worked out what the conjugate momentum was. That was d minus phi. To quantize, we wanted to impose the equal x plus commutators. So we took pi at x plus and phi at x plus, and they were at different points in the minus 1 and 2 directions. And when you calculate that equal x plus commutator, you get minus I h bar. And then there's a delta function setting the extra coordinates, the x minus equal to y minus, the x1 equal to y1, and the x2 equal to y2. So that's how we would quantize the theory. And we also defined a Hamiltonian. So the Hamiltonian was the integral of the Hamiltonian density. It was an integral over x minus x1 and x2. And then what was the Hamiltonian density? Well, the usual formula is pi phi dot minus the Lagrangian. So here phi dot is replaced by d plus phi. So the formula was phi d plus phi minus the Lagrangian. And that was the result that we got. Now, all of these formulas should look very natural to you, and you should be able to explain to understand most of these formulas as just the rule that you replace phi dot by d plus phi. Let's develop a few more things in light front quantization. So the first thing that I want to point out is, usually our metric ds squared, we're used to writing dx naught squared plus dx1 squared plus dx2 squared plus dx3 squared. So I've chosen here the mostly plus metric. You're very welcome to take the mostly minus metric if you want. And the way that we would write this as, we think about this as eta mu nu dx mu dx nu. And dx mu is nothing but the first component is dx naught, we've got a dx1, we've got a dx2, and we've got a dx3. In the eta mu nu dx mu dx nu, mu and nu are summed. And what are the components of the metric? Well, the metric looks like a diagonal matrix. It's a minus 1, naught, naught, a 1, naught, naught, 1, naught, naught, and finally all noughts except for that 1. If you look at the rows and columns of this metric, they are labeled as 0, 1, 2, 3, 0, 1, 2, 3. So this is all stuff that I think that you're very familiar with. Now let's rewrite this in light cone coordinates. So we can start off ds squared is equal to, and I'm now going to combine this minus dx naught squared with this dx3 squared. And I'm going to do it as follows. I'm going to put a minus outside, and let's go back to black. I'm going to put a minus outside. I'm going to put dx naught minus dx3 multiplied by dx naught plus dx3. And you can easily check that the two green terms over there match with this green term over here. And then we have the dx1 squared plus dx2 squared. To identify what dx0 minus dx3 is, recall that x plus is x0 plus x3 over square root of 2. So if I divide by a square root of 2 over there, and I divide by a square root of 2 over there, I'll compensate by multiplying by 2. Then, in fact, I can rewrite the metric as follows. So this is minus 2, and I've got a dx minus times by a dx plus. And for example, let me just be completely explicit. The blue ringed thing over here is exactly dx minus. And the thing that I haven't ringed is dx plus. And then we've got plus dx1 squared plus dx2 squared. Good. Okay, now we can say, let's write dx mu to be dx plus dx minus dx1 dx2, and ds squared, as usual, will be dx mu dx nu times by eta mu nu. And we can now read off what eta mu nu is in light cone coordinates. So eta will be the following. And this is something that I want you to check. Just make sure that you agree with this. So it's off diagonal. There's a minus 1 here, a minus 1 here, and a naught. Now, in the metric, there is a minus 2 dx minus dx plus. That minus 2 comes from the 2 off diagonal terms. And then we've got the rest of the metric, which I filled in over there. And let me just point out how the rows and columns of the metric are labeled. They plus minus 1, 2, plus minus 1, 2. Now, getting used to light cone coordinates, I mean, it's straightforward, it's not too difficult, but I just want to point out one thing, okay? So in normal coordinates, you are used to the idea that if v mu is equal to v0, v1, v2, and v3, then v mu down, well, this will have the 4 indices down. But what is this equal to? Well, this is equal to when we raise and lower the naught index, it costs us a minus 1 because of the form of the metric and because we're using the mostly plus convention. So we'll get a minus v0, we'll get a v1, a v2, and a v3. So I think that by now you are very, very familiar with that. Let's write down the analog formula, but in light cone frame. So v mu would be v plus, v minus, v1, and v2, and then v mu downstairs. So we just drop the indices, v1, v2. But now what is this equal to? Well, if I now use the metric to raise and lower indices, there's something pretty interesting that happens. You see, in the light cone frame, the metric is off diagonal and negative. So we get a change of sign, but the V plus downstairs is related to V minus upstairs. And the V minus downstairs is related to V plus upstairs. Then we've got a V1 and a V2. So we not only have to change the sign of the plus and minus indices when we raise and lower them, we also have to turn the minus into a plus. Now, what is the Schrödinger equation? Well, the Schrödinger equation would say I h bar d by dx plus acting on psi would be equal to our light cone Hamiltonian, which I called h acting on psi. Now remember that p mu is minus I h bar d by dx mu. So if we look at I h bar d by dx plus, this we should identify with minus, we need a minus sign, and it will be p plus. And that's the Hamiltonian. Now, we just said if we raise and lower indices in using the light cone metric, so the sign changes, so I get a p, and when I raise the plus, it becomes a minus. So the Hamiltonian actually is p minus. So the time evolution operator, this is u of x plus, as usual, p minus, the Hamiltonian, is an element of the Lie algebra, so we would exponentiate it. Minus I over h bar, there is an x plus, and there is a p minus. What would this operator do? It's a unitary operator. It would map us between our equal x plus slices. This again tells us that these Hilbert spaces for each x plus slice are equivalent. We can identify all of these Hilbert spaces, and then we're left again with a single Hilbert space in which the dynamics in the light front happens. Good. So that's roughly all I wanted to develop about light front compression. We will continue in a minute.